Okay. It is my pleasure to introduce Professor Michał Misiurewicz that will tell us about travel in an infinite desert. Please.
Thank you very much. So first I want to wish Felix everything the best, 100 years, maybe 120 even. And I checked, and he is at this moment 70 years and 2 days old. So I understand that this conference was scheduled for this time very precisely. Okay, and I remember like about 50 years ago, there was a seminar organized by Schlenk. I am not sure whether it was already called the Seminar in Dynamical Systems, because at the beginning it was just called Seminar in Mathematical Analysis. The name Dynamical Systems somehow did not work very well yet. Nobody knew what this was. And there came a young, very energetic student, Felix Przetycki, and he became very energetic up to now, and let's hope for the future. So happy birthday.
Thank you.
And now about the flower. So this flower in English, it's called ironweed, and probably giant ironweed, because it's usually very tall. So this one, I think, was taller than me. Okay, it's still growing there. And Latin name is Vernonia gigantea. Polish name, it doesn't have any Polish special name, so people call it Vernonia. Okay, so let's move to the talk. Of course, it has nothing to do with the talk. It doesn't grow on a desert, probably. At least I doubt it does. So this is my co-author, Will Geller, from the same university. And now, why do we want to travel in an infinite desert? So with Will, we defined coarse entropy, okay, which is something, the boundary between, or common part between dynamical systems and coarse geometry. So what is this idea of coarse? That your space is very big and you look at your space from further and further away. So you start having problems with distinguishing points which are close to each other. The space is metric, so you can measure how far they are. And if you have, for example, a compact set or any set of finite diameter, then you really can think about it as one point. And you get further and further and further, and what kind of persists is what you work with, what you are interested in. So suppose you have a map of such a space to itself. And you don't have to assume that this map is continuous. For example, if the map is like almost continuous, it looks like continuous map. And to give some examples, okay, take the real line and take the integers. From the coarse point of view, this is the same space, because the distances between two consecutive integers are just 1. And if you look from far away, oh, it's like nothing. So if, for example, if you take a map of the real line to itself, just going to the closest integer. This is not a continuous map, but it looks like identity. Okay, so what does topological entropy, when I say entropy without anything, I mean topological entropy. So what is entropy telling us? How complicated our map is when we iterate it. Okay, so here, if we want to define coarse entropy, we want to tell how complicated the map is when you look from far away. So basically, you look at the stretching. And we tried several possible definitions, and all the definitions were not good. It had a lot of deficiencies, and finally we settled at one definition, which is the best among the ones we tried. So instead of orbits, we use delta pseudo-orbits. Probably all of you know what delta pseudo-orbit is, but let me repeat it. So delta pseudo-orbit of length n, it's a sequence x0 through xn, such that if we take the image of point xi, then it's delta close to the point xi plus 1. So we use the map and then make some small error. And again, from the coarse point of view, it's the same as the orbit, because this small jump by delta, it's just nothing. And then how do we define entropy? We define entropy using the similar ideas as with the Bowen's definition of the entropy via n epsilon separated or n epsilon spanning sets. By the way, I say Bowen. Usually people say Bowen-Dinaburg, because the papers of Bowen and the papers of Dinaburg with this definition of topological entropy appeared more or less at the same time, and they were independent. But probably really you should add one more name to this definition, namely Kolmogorov. Because if you look at the paper of Dinaburg, then he just writes this definition. In fact, he writes limit instead of lim sup, but that's not important. But he writes that this was the idea of Kolmogorov. So probably it should be called Bowen-Dinaburg-Kolmogorov definition. So what do you do for the usual topological entropy? You have a compact space, a map of this compact space to itself, and then you look for epsilon separated sets of orbits of length n. And you take the largest cardinality, then you take logarithm of that 1 over n, so you look how it grows exponentially, and then you go with epsilon to 0. But now we have a different situation. Instead of looking with a better and better microscope, we look further and further. So if you think of binocular, instead of looking through binocular, you look through it, but the other way around. So two differences. One difference that we take not orbits, but delta pseudo orbits. But if you want to define the usual topological entropy, you can use delta pseudo orbits, but then you have to go with delta to 0. So here we go with epsilon to infinity. Of course, thinking about epsilon going to infinity is a little bit confusing. So we rename this epsilon and use R. And then we go with delta to infinity again. If you want to define topological entropy using delta pseudo orbits, then you have to take the limit as delta goes to infinity inside, and outside limit delta goes to 0, and outside the limit as epsilon goes to 0. Here we have to switch the limits because we don't go to 0, we go to infinity, and we want this R to be much larger than delta. Okay, and then one can prove that this value here does not depend on the starting point. Okay, for usual topological entropy, you don't care about starting point. Here you have to take care, because if you take all possible starting points, you would have infinity at the very beginning, and the result will be always infinity. Okay, so what we were trying to do with that, we tried to compute the coarse entropy for a class of systems which are given by homeomorphisms of half-line, non-negative reals. And this class of homeomorphisms were such that they were moving to the right. F of x is larger than or equal to x for every x, and sometimes from time to time there was a fixed point. Those fixed points formed an increasing sequence going to infinity. So if you fix delta, okay, and think about a delta pseudo orbit, and suppose you are between two fixed points. You are between two fixed points, and suppose your f moves you to the right by more than delta. Then you have to move to the right because you can go back at most by delta. So once you are between somewhere really between the fixed points, you have to move to the right. But if you are close to a fixed point where you move to the right by less than delta, then it's your choice what you do. You map by f, by less than delta, and then you can move by delta to the right or less than delta, but you can move by delta to the left, or you can move to the left back to the point where you started. So if you want to find a simplified model of this, then you would do, and you want to simplify it as much as possible, what you would do, first, you would replace the real line by integers, the half line by natural numbers. Okay, as I said already, from the point of view of a coarse geometry, it doesn't matter. Now, the second thing is that you have those fixed points, and then if you are between fixed points, you have to move to the right. And you move to the right by 1 because the way you can choose those points in between is really arbitrary. But if you are at a fixed point, then you have a choice. You can move to the right by 1, or you can stay there. So we thought about how to think about it, and we found this. Okay, so we found this nice description. So we are in a desert, which is our set of natural numbers. 0 is a natural number. And we have oases on this desert. They are located at points a sub n. And of course, an plus 1 is strictly larger than an. And there is a caravan. And it starts at 0. And then each day, they have to make a decision what to do. And if they are in an oasis, then there is a choice. You can stay there, or you can move by 1 to the right. But if you are not in the oasis, you have to move to the right, because staying in the desert without an oasis, it's dangerous. So this is our model. And now what we wanted to find out, to compute, what we wanted to compute was the number of different paths of length n. And so here in this model, we also, there in the original model, okay, the path is the same, is the distances are small. So here we are in a discrete model. So simply, we want to find the number of itineraries of a given length. I call it t, not n, doesn't matter. So we have this number p of t. So how many different itineraries, how many different travels can we make given this sequence of oases, the sequence an? And the question, the original question was, is entropy 0 or is entropy positive? And if it's positive, how large is it? So here we look at the number of itineraries, and we ask, when does it grow exponentially? Okay, so let us look at a simple example. So suppose that oases are placed at 0, there is always an oasis, we start an oasis. So it's 0, 2, 3, 5, and then we can find 9 itineraries of length 4. We can stay at 0 all the time. We can stay at 0. I look at itineraries of length 4. We can stay for 3 days at 0 and then move to 1. If we stay only 2 days at 0, we move to 1 on the 3rd day, but there is no oasis at 1. So we have to move again. And we have to move to 2. Now, if we start moving on the 2nd day, we go to 1, then we have to go to 2, and we can stay at 2, or we can move to 3. Now, if we start immediately, so we go to 1, and we can stay, and we have to go to 2, where there is an oasis, and we can stay there, or we can move from this oasis after 2 days or after 1 day. And when we move to 3, at 3 it's also an oasis, we can stay there, we can move. So we get 9 itineraries. Okay. And then we can consider various possibilities of the placement of oases. And we can make numerical computations. For example, if the time is from 0 to 18. So for such strange placement of oases, where an is the nth prime number, then we get such a sequence of length 18. And we can look at different placement of oases, like oasis is every 3rd number, so 3n. And then we get such sequence. And now we look at you look at this sequence, and you look at that sequence, and you see that this sequence grows much faster than this one. But we were looking at time up to 18. But if you make computations and you compute this PT up to time 200, and then since we are considering exponential, we are thinking about exponential growth, then it's not a good idea to plot the graph of PT, but it's good to plot the graph of logarithm PT. And we choose base 10 because it also shows the number of digits here. Okay, here we have 3 digits, so the integer part of the logarithm, of the decimal logarithm, it's 3, here it's 4. Okay, so then we see different picture. So if an is 3n, that's linear, then we have slow growth here at the beginning. We saw the slow growth, but then it grows linearly, really. Now, if we put an at the point, for example, n+1 logarithm n+1, or the closest integer smaller than or equal to that, then it's so-called linearismic growth, and it grows a little bit slower. And if we take primes, nth prime, oh, it grows still slower. If we take quadratic, oh, now you see it grows really slow. and you take exponential, well, that's basically looks like a logarithm or something like this. So we have various types of growth, and we want to see what is going on. So we can look at the whole problem also in the following way. So we can draw this directed graph on non-negative integers where there are loops at an, and otherwise there you go to the next number. So this is the number of paths of length t starting at 0 in this graph. So you can stay, if you are, these are oases, if you are in an oasis, then you can stay or you can move. If you are not in the oasis, you have to move to the next number. So if an is 3n, this graph looks like this. And then you can compute the exponential rate of growth of PT, and it's similar to the computing topological entropy of a Markov graph, a subshift of finite type given its Markov graph. You can see that here you can kind of replace this infinite graph with a finite graph when you have 0, 1, 2, and you have an arrow from 0 to itself, from 0 to 1, from 1 to 2, and from 2 back to 0. So it will be a subshift of finite type. For a subshift of finite type, it's very easy to compute the topological entropy. Okay, and then we have to see what's going on. So the first thing, which is quite simple, that if we have two sequences of placement of oases, an and bn, and we get those numbers of itineraries pt and qt, and if an is less than or equal to bn for every n, then pt is larger than or equal to qt for every t. And the proof, if you look at it, the proof looks very simple, but you have to take into account that we are not assuming that the distance between an and n plus 1 is smaller than the distance between bn and bn plus 1, which would be very simple to prove for the proof, but we only assume that an is less than or equal to bn. So the proof is simple, but not completely simple. But we have immediately the corollary of that, okay, since for every oasis sequence, we have pt less than or equal to 2 to the t, because what is the kind of most dense oasis sequence? Oasis at each integer, okay? And then we have 2 to the t itineraries. So the sequence of numbers of itineraries cannot grow faster than exponentially with exponent logarithm of 2. Here logarithm is whatever logarithm we are using to compute entropy. Okay. And now, what happens if those oases are placed very regularly? So there is an integer L, and oasis is at L times N. So the distances are the same. Then it's really a subshift of finite type that you get, and PT is equal to PT minus 1 plus PT minus L. Because remember, when you start moving from the oasis, you have to move until you reach the next one. And in particular, this entropy, this limit 1 over n logarithm pt, is logarithm of CL, where CL is the unique zero of this polynomial, x to the L minus x to the L minus 1 minus 1, the unique zero, which is larger than 1. And in particular, if oases are placed at 2n, then this is just the Fibonacci sequence, starting with 1 and 2. And some historical remark that this sequence was known much earlier than 13th century, when Fibonacci published something about it. Okay, and of course, in this case, the growth exponent is the logarithm of the golden ratio. But something also historical interesting, that if an is 3n, then the sequence pt is also known. It's known as Narayana's coarse sequence, and it was introduced by Narayana Pandita in 14th century. And sometimes instead of golden ratio for Fibonacci, here people speak about super golden ratio. Okay, and why it's coarse sequence? Because for one of interpretation of Fibonacci sequence is how the population of rabbits grow. But for Narayana's sequence, it's how the population of cows grow. So rabbits can multiply very quickly, they mature very quickly, cows not that quickly. Okay. And the next observation, the next theorem is that this sequence PT grows faster than any polynomial. So here we do not think about the exponential growth, but just about the rate of growth. And then for any n, this limit of p sub t divided by t to the n is infinite. And it turns out that this is a sharp result, namely if we take the function ht, which goes to infinity, there are sequences an whose number, such a number of itineraries grow slower than t to the power h of t. Okay, and the next theorem is that if we have an increasing function of natural numbers, this ht, h of t, okay, that's really the same thing. So, which goes to infinity as t goes to infinity, then so I already said that this goes to 0. Okay, but now that was about linear growth. Now, what happens if the oasis sequence grows faster than all linear functions? It turns out that the number of itineraries grows subexponentially. So if we assume that the limit of an divided by n is infinite, then this entropy thing, the limit 1 over n logarithm p of t, is 0. And the idea of the proof, of course, is to estimate P of t from above and use, since the estimate involves something like I plus k choose k, then we have to use for further estimate Stilling's formula. So why do we have this symbol here, I plus k choose k? Because we can code the itinerary by sequence of zeros and ones. The itinerary finite, I say finite sequence, but I mean, of course, finite itinerary. And we note only the moments when the caravan is in an oasis, because if it's outside, it has to move. There is nothing we can change. So we say, as we put 0 if it stays, we put 1 as if it moves from an oasis. And if we fix time t, then let k be the number of ones and I the number of zeros. And then we get such an inequality. So here the number of k is between 1 and n. Now here I didn't write what n is. N is a number such that t is between a sub n minus 1 and a sub n. So we can have any number of ones when we move from the oasis, not larger than n. And then how many different i's? Oh, not more than this number, where k is already fixed. And then where you put zeros and ones gives you this, and I plus k choose k. And then you can estimate it, and the crude estimate which we use is such an estimate. And then we can use Stilling's formula, and we get that 1 over t logarithm pt is not larger than 2 divided by t times logarithm t plus n divided by t minus n divided by t logarithm n divided by t. And then we see that 1 over t logarithm pt goes to 0. Okay, so we saw what happens if the oasis sequence is linear, but what if it's not linear, if it's asymptotically linear? So first we need a lemma about this function that we already used. So if we take s a real number, previously this s was L and L was an integer. Now it's any real number, but this function has a unique 0, c sub s larger than 1. Okay, that's a kind of strange terminology, but everybody uses it, that the 0 can be larger than 1 because it's 0 of a function. Okay. And then this equation y to the power s minus 1 is y minus 1 to the power s, has a unique solution larger than 1. And this solution is c sub s to the power s. Well, that's just technical lemma. And then we can prove a theorem that if this sequence an is asymptotically linear, So the limit of an divided by n is s, and s is not necessarily an integer. Then this growth rate, limit of 1 over n logarithm p of t, is equal to the logarithm of c sub s. And to prove it, we use the entropy function. Of course, everything I am doing is connected to entropy, and not everything, but most things are connected with entropy. So we use this entropy function, minus x logarithm x minus 1 minus x logarithm 1 minus x. And we prove a lemma that if s is larger than or equal to 1, and we define f sub s in such a way that x divided by x plus s minus 1h, this entropy of 1 over x, then fs of x is less than or equal to logarithm of cx for every x. So this is purely technical lemma. And then we need estimates for the binomial coefficients. So such estimates are known, you can find it, but not necessarily in the exact form we need, and it's not such easy to find them, so we just prove this again. So we assume that k is between 1 and m minus 1, and then logarithm of m choose k is not larger than m times entropy of k divided by m. This entropy is this entropy function for x and 1 minus x. Okay, and moreover, if k sub m is a sequence such that the limit k sub m divided by m equals b, then this limit of logarithm m choose km divided by m entropy of km divided by m, like here, is 1. So you can think about it as a theorem about the numbers in the Pascal's triangle. So you draw the Pascal's triangle, of course, infinite, and you take one ray which goes from the beginning, from the vertex of the Pascal's triangle, the straight line down, skew. Okay, so this is k, this is the slope is b, so km divided by m is b. And then we have nice estimate for logarithm m divided by km in this line in the Pascal's triangle. And then we prove the lemma, the basic lemma in the proof of the theorem, that assume that an divided by n is s for some s larger than or equal to 1. And then the lower limit, lim-inf 1 over n logarithm pt, is larger than or equal to logarithm cs. In fact, it's half of the theorem. Okay, so how much time do I have? 7 minutes. Okay, so to prove it, so we fix this b and set tm equal this number. Now, this number is not necessarily an integer, so we take it approximately. And then this t is between some tm and tm plus 1. And we use lemma 3, the previous lemma, this estimate, to show that lim-inf of 1 over tm logarithm ptm is equal to the entropy of b divided by s plus b minus sb. So we get those estimates. And now if you go through those estimates, you see why there was this strange number here. Because in our estimates, we get the same type of numbers. Okay. And now assume that lim_inf is S, then lim_sup, so that's the second estimate. We had lim_inf 1 over t logarithm pt. Here we have lim_sup 1 over t logarithm pt is less than or equal to logarithm cs. Here it was larger than or equal to. And we do a similar thing. So we use the estimate that we already had, but now we go further in not so crude manner as we did before. And then we use previous lemmas, of course, to go step by step through what I wrote. It would take more time than I have. So we make estimates, 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 and we get this result. And now we know that 1 over t logarithm n is 0. You have to remember that n and t are connected. So here we have the sum to up to n, small n, but n is not independent of t. N was defined using t. Okay, so we get the estimate that we want. Oh, we have plus epsilon, but epsilon is anything positive. That's true for every positive epsilon, so we can get rid of the epsilon. And now we have those lemmas 4 and 5, which are estimates from both sides, so we have theorem 4. And by the way, if we don't assume that the limit is equal to S, but we assume that the lim_sup is equal to S, then this proof gives us one inequality. And all the time here we were considering the limit of the ratio an divided by n. And instead of this limit, we can think in terms of the density of the set of oases. Okay, so we have the standard definition of the density of the sequence. So alpha of n is the number of elements of our set contained in the set from 0 to n minus 1. So integers, non-negative integers less than n. And then the upper density of the sequence A is lim_sup of alpha n divided by n. And the lower density is lim_inf. Okay, if the lower density and upper density are equal, then this is the density of the set. Okay, and it's well known that if that lim_inf of an divided by n is the reciprocal of the density. Lim_inf is reciprocal of the upper density, lim_sup reciprocal of the lower density. And if this limit exists, finite or infinite, then the limit of an divided by n is 1 divided by density, reciprocal of the density. So for example, theorem 3, which was somewhere here. Okay, so we assume that the limit is infinite and then this entropy is 0. So theorem 3 tells us that if the set of oases has density 0, then the number of itineraries grows subexponentially. And in particular, if the oases are placed at 0 and all prime numbers, then since we know that the set of prime numbers has density zeros, then the sequence pt grows subexponentially. And it would be interesting to study the growth of pt in this case, and maybe other cases, not only concentrating on whether the growth is exponential or subexponential, but make some finer classification. Okay, and that's all. And maybe one interesting thing that recently I discovered that when I was about 7 years old, I was drawing a picture of an oasis. So it turns out that maybe subconsciously I remembered about this after those 60-something years and made this interpreted this sequence as in terms of travel in the desert and oasis. I don't know. So thank you.
Thank you very much. Are there any questions for Michał? Perhaps in the conference room?
We have no questions.
No questions. It looks like online there are also no questions. Can wait a couple of seconds maybe.
We have one question.
Oh.
Probably you have said this, but I'm curious, do you know what is the exact rate of PT when the oases are distributed as primes?
One moment. So, okay, so the set of, so for the primes, the set of the density is 0. So the number of itineraries grows subexponentially. So that means that this exponential growth is not, this growth is not exponential, subexponential. So it's 0. But of course, saying that it's subexponential does not give you all the information. Subexponential, but how fast? And that I don't know.
Okay, thank you.
Are there any other questions? If not, then let's thank Michał again. Now, I believe for the people in bed level, there is some small trip. Maybe there is some announcement.
Yes, I have an announcement. The bus will be 4:45. It should be a few minutes earlier, but we'd like to depart at 5:15. Sorry.